Now that we know how to use a z-score to find a probability with the help of technology, either an applet or maybe a graphing calculator, if you take another statistics class, you might learn how to use a graphing calculator to do these things. With the normal distribution calculator, we will briefly discuss what is going on behind the scenes of this process. As we discussed previously, a z-score is a standardized score. It translates the distance between an x value and the mean into standard deviation units. Instead of how far is this x value away from the mean, it's how many standard deviations is it away from the mean. In other words, a z-score is the number of standard deviations an x value is from the mean. Imagine translating every x value into a normal probability distribution into a z-score. What would the distribution of z-scores look like? The distribution of z-scores will also be a normal probability distribution called the standard normal distribution. It has a mean of 0 and a standard deviation of 1, which makes sense because if you're right in the middle, you're on the mean, so you are 0 standard deviations away from the mean. That's why the center is 0. And a standard deviation of 1. Okay. Example, standard normal distribution. Here we compare the normal probability curve for the foot lengths to the standard normal curve. Okay, so the area from 13, that was the last example we saw on the previous page. So, what was the probability that someone would have a foot length greater than 13? We found the area to be 0.0918 with the help of z-scores. So see how that compares to a graph of just the z-scores, not even talking about x values anymore. But the area is the same. So that, I think, oh man, I can't remember, but I think the z-score was 1.33. Is that right? I want to say, I think that's what it was for this example that we just saw on the previous page. So if you think about, this is 1.33 where this dark blue shaded area starts. The area from 1.33 on to the right is exactly the same as the area from 13 on to the right. So if you kind of translate your x values, which represented foot lengths in this example, to z-scores, you're going to get the same exact areas. They match. Kind of interesting, right? Okay. Understanding these probability distributions. Now that we've kind of looked at those graphs, let's see. Look at the values on the horizontal axes. In the top graph, we have the x values of foot length, like we saw before. The mean is 11, so that's the middle. Standard deviation is 1.5 inches. The bottom graph has z-scores on the horizontal axis. And like we talked about, the mean is 0 because you're talking about what's the average distance you are from the mean. Well, if you're 0 standard deviations above or below the mean, that's the middle. With a standard deviation of 1, that's kind of crazy to think about. How many standard deviations are these standard deviations away from the mean of the standard deviations? Oh my gosh. It's almost, we're getting too deep down the rabbit hole here. That's why usually pretty soon after this, it'd be, okay, you need to learn more statistics or more hardcore statistics and calculus to do more. This is starting to get way out there, like the Twilight Zone. Just wrapping your mind around this stuff is kind of wild. Both graphs are probability distributions with area under the curve equal to 1. Areas in the probability distribution for foot length equal the corresponding areas in the z-score distribution. Like we kind of mentioned as we looked up at those graphs above. Compare the two normal curves and notice the following. First, the z-score at the mean for x is 0. This is always true. For example, foot lengths have a mean of 11 inches, so z is, if you calculate a z-score of exactly 11 inches, which is the mean, you're going to get 0. The x value 1 standard deviation above the mean has a z-score of 1, and the x value 1 standard deviation below the mean has a z-score of -1. This is always true no matter what situation you're talking about. No matter what, it doesn't have to be foot length. It could be anything you're measuring as long as it's a normal probability distribution. For example, the foot length of 12.5 inches is 1 standard deviation above the mean, and its z-score is, if you calculate it, you get 1, because that's exactly 1 standard deviation above the mean. Similarly, a foot length of 9.5 is 1 standard deviation below the mean, and its z-score is -1. We can use the area under the standard normal distribution to find probabilities in the normal probability distribution of x. For example, the z-score for x equals 13 is 1.33, which we saw on the previous page, the very last example we saw. The probability associated with the x values greater than 13 is the same as the probability associated with z-scores greater than 1.33. But why do we standardize x values into z-scores and use the standard normal distribution to find probabilities? That's a good question. The applets on the previous page made it easy, but why do we do that? Why don't we use other applets that just use x values instead of z-scores? The answer is really historical. Before the advent of more sophisticated technology, statisticians used tables instead of applets or statistical programs to find the probabilities. So there's just like a piece of paper that came with every statistics book that had this big table and list of z-scores and probabilities associated with them. So it would, since we didn't have x values, because you'd have to have a lot of different ideas, depending if you're talking about foot length, the mean is 11, but if you have a different example, the mean is something else. So it wouldn't make sense to have one standardized table, but standard deviations are standardized, like we said. Yeah, the as long as you have a certain z-score, the probability will always be the same no matter what context you're talking about, no matter what the x values are. So it's kind of the idea, I guess, that the z-score will never change and probabilities associated with z-scores will never change. So they used to have a table. Now we have more technology we can use. They could not produce a table for every possible mean and standard deviation, like we just said. So they simplified the process by standardizing x values and using a single table associated with the standard normal curve to find probabilities. For given z-scores, they could look up the associated probability for values greater than the z-score. Okay, I'm going to move this down so we can read more. Okay, it's starting in current practice. Okay. In current practice, statisticians often do not use standardized curves. They don't need to. Why? Because they have access to more sophisticated technology. I don't need to look it up in a table that's in the back of my book. I have technology to do that for me. So z-scores are more like, well, we've always done that. We've always used z-scores back in the day when we didn't have access to all these calculators and applets and websites and stuff. StatCrunch has a normal distribution calculator that does not require a standardized score, as shown below. We can simply put in a mean and standard deviation of x, and the calculator determines the probability for us. This allows us to skip the step of standardizing the x value into a z-score. So why do we still teach the standard normal curve? Well, frankly, it's because statistics education has not kept up with technology. We really don't need the extra step of finding a z-score and using a standard normal curve anymore. So it's kind of like when your math teacher says, well, what if you don't have access to a calculator? You got to do this division by hand. Kind of like that, I guess. If you happen to only have a table in front of you, if you're on a deserted island and for some reason you have to calculate the probability of something, you don't have access to technology. I don't know. So we just learn it because people had to learn it a long time ago, but z-scores aren't really something you need anymore as long as you have access to certain websites or applets or your fancy calculator.